Hello, can you guys hear me? Welcome everyone to the ACM SF Meetup. If this doesn't look familiar, you're probably at the wrong place. But um, so before we start, I just want to give a big shout out to Yelp for providing us this venue and providing us food. There are some swag outside with Yelp. Feel free to take them with you. It's a pretty cool company. I just will say a few words before I hand it over to Kyle. So ACM is a non-profit society dating back to 1947. My introduction to ACM was through Turing Award. This is the society that gives Turing Award, which is the Nobel Prize of Computer Science. And the purpose we are doing this meetup is to bring people together, some senior individuals, some students, and in different areas of computer science. If you want to give a talk at this meetup, feel free to reach out to me or Ria. We are the co-organizers of the meetup. Our email addresses are up there. And we'll also be hanging out in this area after the talk. Yeah, we have a, so without further ado, I want to introduce Kyle, who is a SRE at Yelp, and he has been working with servers for 10 years. He'll be talking about layers, something that makes systems possible. Over to Kyle.
Thank you. Like you said, my name is Kyle. I call myself just an engineer. I don't actually call myself an SRE nowadays, mostly because I think that I see myself as a generalist, and I see myself as much more than just reliability. I think sometimes when you box yourself in too much about what it is that you work on, when you think of yourself as a reliability engineer, you might neglect other things that, a kind of holistic approach to engineering. So I should probably just update the slide. But yes. Let's talk about layers. It's one of my favorite subjects, as I like to think about it a lot. Let's talk a little bit about Yelp first. Yelp is a company that builds an app that connects people to great local businesses, blah, blah, blah. They're my employer, and I am legally obligated to put the slide up here. We also help ambulance drivers find great local hospitals to bring their patients to. This is a joke. This is not real. Abstraction layers. Yeah, so what does this mean? I'm going to talk a lot about abstractions. I'm going to talk about the principle of separation of concerns. Can anyone raise their hand if they've heard that principle before, separation of concerns? Okay. And for the recording, most of the people in the audience has risen their hand. That's because it's a very popular principle. It seems pretty straightforward. You want to separate your concerns to make it easier to iterate on your things and isolate failures, that kind of stuff. Sounds pretty good. Well, let's see how it looks in practice as we've kind of gone through stuff. First, to get your mind flowing about thinking about layers, I'd like to introduce some inspirational quotes. Dijkstra says that layers are, in the end, a way to be absolutely precise in your thinking. Cool. Spolsky, a very famous quote, says that all abstraction layers are, to some degree, leaky. We'll talk about what that might mean. David Wheeler is one of my favorite ones. That he says that every time you add an abstraction layer, it will usually creates another problem. And that happens sometimes. We'll talk about it and we'll see some examples. Before I go too far, I want to introduce another person who has thought about this a lot more than I have. His name is Rich Hickey. He has a great talk called Simple Made Easy. So if you like thinking about this kind of thing, I highly encourage you to see this talk, mostly because it's kind of the opposite of what I'm about to tell you. So, I think that one of the great ways that an engineer can expand their mind and exercise their thinking is to see two different ways of thinking and then kind of synthesize their own opinions, their own, conclusions. So, Rich Hickey, he's a pretty smart guy. I'm going to go through some examples of abstraction layers, and I want you as the audience to think really hard about these layers as we go through them. Some of them are going to appeal to some people Some will understand some examples better than others because some people are in the industry, some are academic, blah, blah. Let's talk about DevOps. DevOps is kind of old nowadays. It's almost 10 years old. This is John Oswald from Flickr. This is one of the first DevOps-y presentations about deployments and rapidly deploying. When I think about DevOps, I think about the layers of people. We put people in different layers, and they do different roles. Let's take a look real quick at the roles of the kind of traditional full stack thing you do. Going all the way to the top, the highest level business thinking stuff is the PMs, the product managers. They're thinking about the features. They go down to the user designers who build like wireframes and mockups. The lead developer might make the big tasks, epics, and that kind of thing for the developers to code up. Maybe they make some unit tests. QA does their job to make sure that you're sending out quality code, and then the release engineering team may get a green build and then hand it over the wall to operations to deploy into prod. Hopefully everything goes great. For those of you who have been in the industry, you might be looking at this and kind of like being really skeptical because nowadays we think this isn't such a great idea. Nowadays we don't think that it's a great idea that there's a separation of concerns between all of these different layers. All right, what's up with that? So every time that you see a really pretty graph like this with lots of colors and the like well-spaced thing, I want you to think this in your head. In fact, I even want you to say it with me because I say it all the time at work if you're on my team. So ready? I would like you to say, what if we got rid of some of the layers? Ready? 1, 2, 3. What if we got rid of some of the layers? Yeah? I mean, look at that. I mean, like, what if we did get rid of some of the layers? Well, the thing is, in real life, these are people. It's not so simple. They're not just in distinct layers. There's groups and there's teams. I like this enterprise IT architect diagram here. I love the DevOps box in the middle. For somehow it's just like connected or something. I don't know. But sometimes we think that those kind of layers operate like this, where they're like puzzle pieces that are interlocking. In practice, it's really finger pointing all the way down. People pointing out their fingers. And again, if you're in the industry, you know exactly what this is like. And this is kind of where DevOps comes from. It's a reaction to this kind of thinking. Well, what if we did merge all these layers together? What would it look like? Well, it would look like DevOps. That is the extension of that kind of thinking into this domain. Devs are now responsible for their code, and they're responsible for their own quality assurance, and they're responsible for getting a green build. And if you're really cutting edge, you're also responsible for deploying the code that you wrote into production and making sure that's healthy. Heck, maybe you're on the hook for the pager if it starts to break. We do this at Yelp, so I'm proud to work at Yelp where we are doing this, and mostly because we believe that this is a good idea, but good for what purpose? Good for who? So yeah, there's no separation concerns here. We expect the developers at Yelp to be concerned with all of these layers. Is it good? Well, let's look at what the outcome of this kind of thinking is when we apply it to humans. We definitely get increased performance. So that original slide from Allspaw, the increased deployment frequency is definitely a thing that comes out of this. When you have one team that's responsible for all that stuff, you can deploy very frequently. You don't have to pass it from QA to rel engine stuff. Ownership is a big deal. So now that you're the single team, this whole like finger pointing and throwing things over the wall, that goes away because you're on the hook and the buck stops with you with the build. It is harder to hire. Now you have to hire somebody who can do more than just code. They need to think bigger. This is kind of tough, but we've kind of accepted this is like a thing nowadays. Developer complexity, developers do need to learn more things. Now they might have to know about Jenkins, they might have to learn about Kubernetes, they might have to learn about all sorts of other stuff, whereas before they didn't have to. Inter-team communication overhead is a big thing because now you don't have a dedicated ops team, so maybe there's some expertise that you lose. So there's some trade-offs, but again, as engineers, especially as ACM members, your job is to make these trade-offs in engineering, and this is one of the trade-offs that the industry has made over time. I'm pretty sure it's a good call, but it kind of remains to be seen if this is going to keep moving. There's lots of different DevOps patterns. So everybody got that example? It's not quite engineering, it's people, but it's an example that I'm going to segue into file systems, a much more hardcore, lower-level example of layer smashing. Ready? Ooh, look at this one. Okay, so classic kind of file system-y stuff on a Linux system. Let's start at the bottom. You got these raw block devices. So if you used a Linux system before, you may know that there's like dev SDA or your NVMe drives, that kind of thing. And on top, sometimes you'll do a software RAID. So that would turn into an MD block device, something like that. And eventually you do need a device mapper. So LVM is the technology in Linux to do that. So you'd make that layer on top. And then if you want encryption, so if you want your code, your zeros and ones to be safe, you would use encryption on top. That goes on top of the LVM, not below it. And then on top of that, you need an actual file system, of course. You need the files, you need real files on top. So that would be ext4 is just an example. And then, of course, the files that are inside the file system go on top of that. So this is how you would construct a full file system with all the features on a Linux device, a Linux server. Are you guys thinking what I'm thinking? What if we got rid of some of the layers? Maybe this separation of concerns isn't such a great idea. I mean, maybe it is, maybe it's not. But what would it look like if we did that? Well, I can give you an example from the industry. It's called ZFS. ZFS is a file system where the designers said, screw separation concerns. I don't care about separating all these things. You know what? I'm going to put all of it in one big layer. So ZFS does it doesn't like replace the raw block devices, but it operates on top of raw block devices. It does its own equivalent of LVM. It has its own pools. It has its own checksums. It does encryption. It does its own RAID. Of course, it's not traditional RAID. It's Z-RAID. And then files on top of that and all that good stuff. And again, you have files when you're done, sure. But as far as all those other layers, they've been smashed into ZFS. So ZFS is absolutely not concerned with the separation of concerns. They're concerned with everything. ZFS is absolutely concerned with the status of the raw block device as much as it's concerned with the checksum of the literal file that you're operating with. Is this a good idea? Is it such a great idea to go against the common wisdom of separation of concerns, the principle of separation of concerns? I mean, I'm pretty sure I read that in some book or something. It's probably a good idea. But what do we gain? Again, engineers, we need to make trade-offs and we need to make sure that we're doing the right thing for the right reasons. ZFS does give us a lot better error recovery. So if you've ever used a traditional file system with classic software RAID, because of the distinction in the layers, the software RAID layer doesn't know about the files that you have on top. It's not concerned with that. So when you do a RAID rebuild on a traditional file system, it has to sync over all the zeros and ones from one hard drive to another, if it's like RAID 1. It's a mirror. So it must sync over every single 0 and 1, and it has to be sure. Even if those zeros and ones don't have any files on them, they're not corresponding to any files, the RAID layer doesn't know and doesn't care, so it has to do that anyway. But on ZFS, it knows exactly which files correspond to which zeros and ones on which RAID block devices. So it can do a much more efficient sync, and it can tell when it's wrong because it's doing checksums on files. So if there is corruption at the lower block device, it can detect that. Traditional file systems cannot because they are abstracted over the raw block devices, and they just have to assume that the lower levels are responsible for making sure that the integrity of the zeros and ones. ZFS does not make that assumption. It's concerned with that. So better error recovery. Deduplicating is efficient in ZFS, and it's not very efficient on the other layers. The reason this is the case is because ZFS can dedupe. It knows which files correspond to which blocks. So on a per pool basis, or even I think on a per file basis, you can say, I want 3 copies, and it can make that happen. Whereas a RAID device doesn't really have a concept like that. And it can't, again, because of separation concerns. Snapshots repair, similar kind of deal. Snapshots on a ZFS file system are super fast because, again, it knows where the files are, it knows where the zeros and ones are, and it can just make a snapshot where that's pretty much impossible. You can make LVM snapshots, but again, it doesn't really know where the files are on there. Ooh, some bad news. All the tooling that you know and love is now incompatible because ZFS has its own stuff. It's got its own ZFS RAID, it's got its own ZFS repair. You can't just run whatever. So that's a bummer. There's some other legal issues that I used to have on here, but it's no longer the case. But it's a brand new kind of paradigm. So that's a big kind of barrier to entry. And guess what? For all of those benefits, ZFS still is not an extremely common file system. It's not the default in many places. It's kind of a big beast of a file system because of that, so we usually don't use it all the time, even though it has all these benefits. So again, trade-offs. We have to figure out when it's useful to use a full-fledged file system like ZFS that's concerned with all this stuff, and when to use something that we just kind of don't care about. So I've introduced a couple examples. Now before I go on, I would like to introduce a new concept. I'm going to call it the sympathetic abstraction. It's where we build these things where the layers kind of leak over to each other. Maybe they're smushed together and we call it the same thing. Internally, the ZFS has layers. They're different functions, classes, modules, that kind of stuff. Sure, they're in one code base, but they all kind of leak around because they can kind of inspect each other. There's no strong separation concerns. I really like this blog called Mechanical Sympathy. That blog, Mechanical Sympathy. This is where I've kind of I kind of like grew on me this idea that abstractions can be leaky on purpose. So I'm going to call abstractions that are leaky on purpose sympathetic abstractions because they're sympathetic to the layers above and below. Okay? You deal with sympathetic abstractions all the time. You don't even know. This is a screenshot from just SSHing someplace. SSH is a protocol agnostic doohickey. It's got, it's traditionally you might call this a layer 7 protocol, sure. Look at it setting TCP node delay. Now, you raise your hand in the audience. Do you know what this is? Does anybody know what this is? Just a few hands? Okay. TCP node delay is turning off Nagel's algorithm, or it's turning on Nagel's algorithm. I can't remember. It's the thing that allows it to not queue up packets in a TCP stream. The reason we do this in an interactive SSH session is because you want your keystrokes to come back really fast. So we tell TCP to not wait. If we have a packet to send, we give it to TCP and we say, don't wait for any more packets. Go ahead and just send it. I promise, it's okay. We do this because we want our SSH sessions to be, snappy. So what's up with this layer violation? Why is SSH setting TCP-specific options? It should be not concerned with its transport, if you ask me. But in practice, we got to get our jobs done. So SSH would be pretty lame if we didn't dive deep into layer 3 or layer 4 and turn that off to make your SSH session work. Fine. How about this one? Here's Cassandra, and somehow there's an option to let it know what kind of hard drives you're using. Cassandra is, of course, a database, and it is pretty concerned about what kind of hard drive you're using. They didn't have to do this. They could have just said, hey, it's not my problem. Whatever block devices you're giving me, they're going to work. It's your job to tune them however you want or something. But in practice, out of performance needs, they need to know because Cassandra is kind of sympathetic to the hardware that you're running on. So my sympathetic law of abstraction that I'm going to coin, I would like to say that over time, the layers we build tend to become more sympathetic or merged or whatever in the pursuit of performance for different definitions of performance depending on the application. So as we saw in the example with DevOps, over time, the industry has kind of merged or converged those layers together in pursuit of the performance of deploys, faster business stuff, features out, that kind of stuff. In the other example, you saw that file systems got merged in pursuit of performance when it came to, I guess, reliability and that kind of stuff. So different ideas of performance, but they become merged over time. Whereas before we started off with really clean separation concerns, we kind of said, maybe we don't need that many. Maybe it'd be better if we just merge them a little bit. So let's keep going. Let's talk about a protocol that's near and dear to all of the Yelp engineers in the room, of course, because it is our bread and butter and it pays the bills. HTTPS. This is an extremely common protocol. Of course, it runs, powers the World Wide Web. To talk about that, I'm going to reference the OSI layer model. Can I have another show of hands for those people who have heard of this model and they know about it? Maybe they learned it in school. Okay, for the recording, it looks like about 3/4 of the audience raised their hand. This is not exactly, you don't have to know this model to get your job done. It's kind of one of those, it's a little academic, you might say, but it is a very useful model for debugging and understanding internet technologies. Let's talk about it a little bit. It was published in 1984, so 35 years ago. I guess 35 years ago. Way early. So way before Yelp.com existed, way before Instagram stories, and way before Snapchat, we were thinking about these kind of things, and we were thinking about how we're going to build these protocols for the long run. Well, we decided to sit down and write down this spec, and you can buy it for a mere 175 Swiss francs if you want the actual spec from 1984. But yeah, it basically lays out these 7 layers. So this is how we understand how we build our network protocols. We start with the physical. We go up to something called the data link, and then the network, transport, session, presentation, application. Not too important what these actually are, but what's important is to understand that this is the foundation for many of the protocols we use today, sorta. So let's look at that protocol. Let's look at that protocol stack in terms of a modern connection to, say, Yelp.com. The bottom layer is physical, so that means literally the wires, or in this case, if we're connecting over laptops, it'd be Wi-Fi. It's still physical. You got radios and stuff. So 802.11 is the name of the protocol that we use at the physical layer. The data link layer is also 802.11 for some reason. So when I first started understanding Wi-Fi, I was like, this doesn't quite make sense. Usually there's one below, and usually it's like 10 base T and then Ethernet top. But they merge layers in this case, so I just let it slide. I mean, whatever. The internet protocol is layer 3, definitely. That's always been what layer 3's been. There's other layer 3 protocols, but the internet protocol is the one we use nowadays. In the case of HTTPS, TCP is our layer 4 protocol of choice. It's reliable. Layer 5 session. HTTP is stateless, so we don't need any sessions. The Wikipedia said that, so I just put it on a slide. HTTP is stateless, so I hear. But of course, everyone in the room who's ever operated any web server knows that, that's a joke. Okay, the presentation layer is SSL, mostly because I didn't know where else to put it. SSL, it didn't fit on layer 5, and it doesn't fit on layer 6, so it's got to fit on some of these layers, right? And then, of course, layer 7 application is HTTP, because, by definition, it goes to the top. So you might be thinking to yourself, well, first of all, I hope you're all thinking what I'm thinking, right? What if we got rid of some of these layers, right? Why is Kyle's having such a hard time fitting these boxes? Because, it doesn't seem to fit in here. And, when I was in school and I learned about this OSI layer model, I was kind of enamored. I thought that the model was so great. It's such a perfect way to think about troubleshooting and where the packets go and going up and down the stack as you do this thing. And even today, when I do interviews or talk to other people, we say oh, that's a layer 4 problem, that's a layer 3 problem. This is a great way to understand our protocols. But I'm telling you, in practice, it doesn't quite fit. Here's the real story. I'm telling you, it's from the Wikipedia. The IETF is not concerned with strict layering. They are purposely not concerned with this. This blew my mind. I was like, what are you guys talking about? This is blasphemy. It's not intended to be OSI compliant. So what is going on here? Historically, we made the OSI model. We thought it was a great idea. But in practice, engineers are tending toward merging layers together and making them more sympathetic to each other and realizing that the principle of separation concerns maybe isn't the best when you need to actually get your job done and get stuff done. In practice, there were many different models. Not all of them had 7. So just depending on who you ask, they just conceptualized our networks in different ways. To me, as the philosophy major in me says that this is a map and territory mismatch. You might say that these are maps, and they're trying to write down what the territory is like, and the territory is, of course, real life. And in real life, the layers aren't this distinct. They're a little blurry. But we try our best to make maps of them, but they're not accurate. So let's look at this again. Again, what if we merged all the layers together? Yes. What if we did do that? What would it actually look like? I'll tell you what it looks like. Did it. And it's called Quick. Show of hands again. Has anyone heard of the Quick protocol? Okay, maybe 25% of the room. Believe it or not, you use this every day, almost certainly. This is the protocol that powers most of the Google web technologies, YouTube, Gmail, that kind of stuff. If you don't believe me, because I didn't, prove to yourself when you go home, run Wireshark or TCP dump or Ethereal if you're old, whatever it is that you run to see your packets, and I promise you'll see UDP connections, and they will surprise you. You won't be able to inspect them, of course, because layer merging. So in the new world, if you're connecting to a modern web property that's using Quick, we just give up and we say Wi-Fi is layers 1 and 2. The internet protocol is still layer 3. God bless America. Layer 4 is UDP, not TCP in this case. So the only reason that the Quick developers did this is because they needed to actually get through firewalls. They needed to actually get transported. And they couldn't make up their own layer 4 protocol because all of our boxes only support either UDP or TCP. So they had to pick one, and this was the one that gets out of the way the most. If they could, they would have just not even had layer 4. But in practice, they need to get transported across the internet. So UDP it is, and then everything else is all above. So Quick is totally concerned with its own encryption, its own session management, its own multiplexing, its own error correction, everything. In fact, Quick does not even care about layer 3. It has its own session identifier. It doesn't even care what IP address you come from. If you roam from your Wi-Fi to your mobile to 3G or whatever, your session will still resume as if nothing ever happened because, again, it doesn't even care about layer 3. It doesn't care about layer 4. It doesn't care about what UDP port that you're inbound on. It really just cares about that UUID in your quick session. So the quick developers are just thinking to themselves, what if we merge all layers together, screw layers 1, 2, 3, and 4, and we'll do our own thing? And they did. No separation concerns up here. They're concerned with everything. Well, it's hard to argue with the results. So Quick is actually very great as far as network protocols go. It has some really great properties with regards to error recovery, zero round-trip time SSL, TLS establishments. Bandwidth is just off the charts because it's just so efficient. You don't have to worry about TCP backoff and stuff. It's pretty good. The numbers don't lie. But there's some costs. So let's, again, engineers, trade-offs. Somebody made this call to do this in pursuit of performance. But let's look at the trade-offs. Roaming sessions, like mentioned, your phone could just switch and it's none the wiser. Quick doesn't care. Zero round-trip handshakes. If you ever work with SSL, you know that you need a lot of back and forth to even establish a session. There's TCP and there's the SSL handshake. Quick, you can do that with zero round trips, which means the first packet that you send to Quick is the establishment. There's no round trip necessary, which is unbelievable. We can't get better than zero. Better throughput, better loss recovery. It's just better in many ways. Downside, none of your tools work anymore. Just like in file systems, the tools that you know and love don't work. You can't just run TCP dump and see your HTTP headers anymore because, again, they're all encrypted and they're all like encapsulated in the UDP, the Quick protocol. This is so avant-garde that few companies have even dared to ship this. I'm pretty sure only Google and Cloudflare have had the guts to say, yeah, we're going to just use this totally different protocol. Yeah, there isn't very good tooling. There isn't some like gold standard Quick web server yet. There's a couple random libraries, but in general, it's a little iffy. And this is a big one here. You have to have faith in Quick crypto. Now, if you've been through Heartbleed, you may have less faith in the non-crypto, but to think that they would be brazen enough to be able to do crypto correctly themselves, I don't know, it's kind of a big deal, and we're going to give that up if we're going to move to Quick, because again, it's concerned with its own cryptography. Something to consider when you're doing trade-offs. But in pursuit of performance, as an industry, we've done this, and it's pretty good. And I personally look forward to our quick future. Let's talk about another example, another hot button one in the industry, microservices. So, classic Rails application. Model view controller, standard textbook example of how to do things. MySQL server, totally great. Like MySQL is the gold standard of open source relational databases. And then users, this is a really a beautiful architecture diagram of a Rails app. Many startups have started exactly like this. Things like Twitter is my canonical example of a startup that started up as a Rails app. Are you guys thinking what I'm thinking? Nope, you're not. What if we added a bunch of layers, right? No. So we're not going to remove layers in this case. We're going to add a bunch. Why? Why are we going to do this? Well, in practice, the Twitter has had terrible reliability in the past. Until for the past 10 years, until they've moved their architecture away from the Rails monolith. Why do they do this? Well, what does it look like when they did do this? Well, they separate all of the components of the Rails monolith into individual pieces and with their own data stores. So this allows them to iterate on each individual component faster. It allows them to kind of focus and scale and increase reliability for their individual pieces. You can use the right data store for the job, so different data stores have different properties, so that's good. You can add more developers, so you can kind of throw developers at different pieces, and it's a lot easier than having 1,000 developers working on a single Rails app. Of course, it starts to look like this because they start to talk to each other. And if this was happening in the Rails app too, it's just it was function calls, and now it's network RPCs. And eventually you get this kind of Death Star diagram where you have thousands of microservices, and they're all talking to each other, and you can't understand what the heck is talking to what. Yelp may or may not look like this. And certainly Netflix, is kind of the big proponent of these kind of things. And you'll see on Twitter people kind of bragging about how complex their microservice call stack is. What has happened here? Well, we decided in this situation to not merge layers together, but to split them out. And I bring this example up because not only is it an industry trend, but it's also an example where under the right circumstances, we need to increase performance for a different definition. We need to increase performance for throwing people at the problem. So we lose the ability to make cross-cutting changes. In a Rails app, you can make one git commit, and you can change function calls and interfaces, all sorts of stuff. But when you have all these microservices and you need to make a change, you need to stage that out. You might need to change the schema or the API of one service, change the caller of another, deprecate from a V1 to a V2, lots of complexity. The deploy process, of course, was simple. The Rails app, you have one thing to deploy. Now you have all these microservices. The Polyglot stack is, you could see that as a pro or con, but now it depends. The unified tooling, of course, in the Rails ecosystem, you've got a lot of things going for you, and now when you're going to stray, you have to reproduce that tooling or figure out bespoke tooling for each one. On the plus side, you can scale out your components, so you can scale individual pieces, but the real plus here is that you can scale out development. It's really hard to have 1,000 Twitter engineers working on twitter.com when it's one Rails app. So all other constraints being equal, what can they do? Well, they decide to scale out the layers, not merge them together, again, for a different definition of performance. So this is kind of a counterexample, but I want you all to keep it in mind as we talk about other industry trends like Kubernetes. So let's talk about Kubernetes. So Kubernetes, if you haven't heard of it, is a very popular and up-and-coming container orchestration framework. Yelp's cool too. We use it too. It's pretty good. So let's use all of the examples that we just talked about and use our brains to evaluate Kubernetes in the framework that I've kind of laid out in terms of layers, separation of concerns, performance, that kind of stuff. In order to do that, we need to talk about the classic deployment method before Kubernetes. So classic deployment, we would have maybe on Amazon, you would have a bare metal server, so you'd have like, an EC2 instance. Good. One layer up, you'd have a VM, so your VM would be running on that EC2 instance. This is classic kind of cloud deployment stuff, so you have a VM, sure. One layer up on that, we have an operating system, so you got to install Ubuntu, whatever. And then on top of that, you'd run your real application. So maybe you're a Java shop and you run Tomcat, or maybe you're a Python shop and you run, I don't know, Flask, or maybe you're a Ruby on Rails shop and you run Rails. But for the most part, your stack looked like this before the Kubernetes world. We had either bare metal or VMs, operating system, and your application code. Pretty easy to understand. What if we added even more layers to this? Is this a good idea? Well, hold on your hats because we're about to. This is what it looks like in the Kubernetes land. We added a bunch of layers here. We have the bare metal before, same. We have a VM, same. Still running an operating system. Got to run an operating system, right? And then we added this container orchestration layer, Kubernetes. Now, if you haven't used Kubernetes in production, it's kind of a beast. There's like a whole nother language to describe all the concepts, and you got those things. You have these pods, which are collections of containers. You have the containers themselves, and you can use Docker. You have all these other things. You have network overlay networks, and like secret providers, and all sorts of stuff. It does a lot of things. And then finally, in the end, you get some process, your java-jar or whatever it is that you're running inside of Kubernetes eventually, and it runs your actual code. So we added a bunch of layers, but why? Why did we do all this? Why wasn't it so great when we were back in the good old days of just having a VM and running our application on top? So easy to understand. Well, we did this for a reason. There's a reason the industry is doing this, so let's kind of analyze that. Well, yes, so what if we got rid of some layers? The thing is, as the industry evolves, Kubernetes is giving us new capabilities that we didn't have before. The particular capability it's giving us is the ability to think outside the server. We can think beyond what a VM is. So in the past, if your application needed 4 CPUs and 16 gigs of RAM, what you would do is you would get a VM from Amazon or your cloud provider, or heaven forbid, you would have to provision some bare metal with those specifications. Now, maybe you had to over-provision because of reasons and that kind of thing. But for the most part, you had to get a VM that matched your requirements. Kubernetes and other container orchestration systems are allowing us to use a server a little bit more fully because we can run multiple workloads on it and not really be concerned about which version of the JVM is on there. So I think one of the first layers to go as we explore this space as an industry is going to be the idea of splitting the VM up. If you think about it, one of the only reasons that we split up the VM into like bite-sized pieces is to match the workload of the application. In the Kubernetes world, we don't have to do that because we can run multiple containers on the box, and we can just fill it up until it's full, for the most part. So this screenshot is an example of the Metal instances from Amazon where they don't have hypervisors running them, or at least not software ones. So this is an example where you can get the full server from Amazon. You're literally running on bare metal. And if you've been around in the industry long enough, like I have, this is kind of mind-boggling because we've kind of come full circle. We've gone from like real metal to VMs being just like the amazing technology that's going to change everything. And now Amazon says, hey, you don't have to use VMs anymore, so you don't have to. You'll get the full performance, so no performance overhead of having the VM, and you get all of the CPUs instead of having some reserved. So yeah, this is the future, I believe, of real Kubernetes deployments on clouds because, again, you don't have to slice and dice your VM just to fit your application on it, thanks to containers. So I think this is the first layer to go. So hardware, VM, to me it's the same layer, or at least it's going to be the same layer in the next 5 to 10 years. What about the next one? What if we did merge all the layers together? Well, the extreme case of this would be something called a unikernel. If you haven't heard, a unikernel is the idea of, it's literally the extreme of this idea, and it's bundling up your entire application, all the libraries, and all of the kernel that's required into a single process space and that kind of thing. It's literally one binary that you load onto the Metal or the VM, and it runs fully. It's a pretty unique idea. It hasn't really taken off the industry, but it's got some interesting properties. But I'm here to tell you that I don't believe this is the future. As much as you may think that I am such a big fan of layer smashing, I don't think that we should be smashing these layers together. And the reason I don't think that is because I think we lose something. I think what we lose is the ability to separate out the things that we care about versus the things that are considered infrastructure. I believe this separation is real and not something that we want to merge together. I think the real future is this. So you might call this the functions as a service, AWS Lambda. Some people call this serverless, but I really hate that term. I'm never going to use it again, so mark my words. I'm going to call this functions as a service. Let's talk about the layers here. If you're going to be running functions as a service on Kubernetes or on Amazon's doohickey, you're going to have your hardware or bare metal or VM or whatever on layer 1, 2, 0, whatever, sorry, 0, 1. You might be running either Amazon's Lambda stack or your own Kubernetes functions as a service stack. This is a little new, but I believe that this is going to be more mature in the future as Kubernetes comes of age. And then on top, you have this container. And now in Amazon, they use Firecracker, which is a open source kind of like fast VM loading doohickey. And then if you're on Kubernetes, you're going to be using Docker. And then finally, you get your process, your code again at the very top. Now, why is this any better than this? Why is Kyle saying that separation concerns is now all of a sudden really important? Well, I think this is the case because by only focusing on layer 7, you're giving developers the ability to not worry about the stuff below, and you're giving them the gift of speed. This is kind of slow, and worrying about all the things inside is kind of a pain. In this world, you only have to worry about the top, and as long as the infrastructure team is doing a great job, you don't have to worry about that, the layers below, but they do leak up. They leak up because the layers in green are tightly intertwined with your layer 7 process. And in practice, this manifests as things like Envoy as service meshes and secret providers and other Kubernetes things are integrated with your thing, and your code becomes kind of Kubernetes aware or cloud aware or just mesh aware, or just it begins to get tighter and tighter integrated with your stack. I see this as an inevitable kind of thing as we, again, pursue performance, for some definition of performance. So are we back to where we started? Where is the mechanical sympathy here? You remember I mentioned that we're seeking performance, and layers are mingling and getting better at talking to each other, just like the other examples. Where's the mechanical sympathy in this example? What happened to layer smashing? Why are we doing this? Well, I think we're doing this because of that, or this is the real future to me. This is where the layers really come smashing together, and it's not in the pretty boxes that you saw before. It's a little bit more nuanced, so let me walk you through it. I think the future is really the smashing of the routing and dispatch layers. So in the classic example, remember you have a classic application, you have a load balancer, and you have requests that are coming in. These are the real bread and butter of what your application is serving, your HTTP request for Yelp.com. They're being load balanced to your set of VMs running your application code. Again, classic cloud deployment. This is like textbook deployment stuff. In the new world, it's not quite the same. The dispatch and API gateway and routing are kind of the same layer. In the Kubernetes world, with functions as a service controllers and that kind of thing, they are aware of each request. They know about the application that's running underneath. They know exactly how many requests they've sent to your different applications. They know what kind of application your thing is running. So maybe the runtime environment knows that you're running a Node app, so it knows how many requests it can handle. Maybe it's a Python application, so it knows how many workers they have. So the thing in red knows how many simultaneous requests can be served to each one of those. And if it's running out, it can just launch more. So the layer at the top is very sympathetic to what it's routing to beneath. On the left-hand side, that's not the case. There's a strong separation of concerns between the load balancer and the servers that are underneath. If you ask Amazon to make it so that the load balancer could launch new servers for you, they'll tell you no, because that's not really within the scope of what their Elastic Load Balancer product does. It's just not concerned with it launching servers. It just load balances things. You have to tell it what to load balance to. You can certainly launch your own servers and then reconfigure it via the API, but it's just not like that. In this case, they're the same thing. The routing and dispatch are the same thing. They're not only empowered to route requests to the right application, but they're also empowered to launch more copies of the application if it sees fit. This to me is the kind of extreme and perfect example of where the layer smashing needs to happen at the right layer. Let's talk about other examples of where another reason why I think that this is the future of this sympathetic abstraction stuff. And a classic deployment example of deploying something like MySQL. If you try to deploy MySQL on an Amazon autoscaling group, you will have a hard time. The reason this is the case is because an autoscaling group has no idea about MySQL topologies. So if it launches another MySQL server in your autoscaling group, it will have no idea that it needs to maybe replicate from another one, or needs to be promoted, or maybe the topology needs to be adjusted, or maybe that your application needs to discover it but not send requests to it yet because it's not caught up to date. So there's all sorts of nuances here. And again, as an industry, we've done our best to work around this and set up extra code to work around the fact that the autoscaling group doesn't care that you're running MySQL. It just launches new servers. You need to tell it what to do. And then it's left as an exercise to the reader to configure all these things. In the new world, in Kubernetes, we have this concept of the operator. The operator is a piece of code that is absolutely concerned with what your application is and how it's configured. But not only that, it's also empowered to launch its own containers. So we have plenty of tools that can configure MySQL. Great. But not many of them can launch their own copies of MySQL. It's just not part of their concern. They're just designed to configure MySQL servers that you give it. It can configure replication, it can configure backups, it can do topology hierarchies, but it's just not normal that the tool like this would be able to launch its own MySQL servers for you. But a Kubernetes operator certainly can. Not only is it responsible for configuring the MySQL server, but it's also responsible for launching that server in the first place. Now I say server, I really mean container, but it's more or less the same. This application-aware abstraction layer is absolutely concerned with the fact that you're running MySQL, and it really cares about all these things. And on the other side, although MySQL may not be Kubernetes aware yet, in the industry we're running a lot of sidecars. So if you've heard that term, that's the act of adding additional processes next to MySQL to make it more Kubernetes aware or mesh aware or whatever. So we're kind of like bolting on extra stuff to make MySQL sympathetic to the fact that it's running on Kubernetes. In the long run, I expect our applications to evolve to be more holistic. But that's the feature of the industry, if you heard it from me first. Now, the operators in practice are very new and raw. So this is not something I encourage anyone to just jump into. At Yelp, we are jumping into it, but we are trying our best to make sure that we do things kind of slow and steady and not bring down the website. But this is definitely the future of infrastructure layers at Yelp and certainly at the industry as well. So keep your eye on the fact that Kubernetes operators are evolving. And again, remember the reason that this is happening. This is not the first time that we've had MySQL-specific integration tools, but this is the first time where we've had a tool and a framework, and the layers have been smashed together in such a way that the tool can do everything it needs to do a full MySQL deployment, set up replication, launch whatever it needs. Over time, you will see operators pop up for all the types of distributed systems that we have ever. And then as new systems come online that were kind of born in the new world, you'll begin to see them become Kubernetes native. And they're not going to need special sidecars. They're just going to know that they're running on Kubernetes. They're going to be sympathetic to the fact that you're running a platform that is empowered to launch new things. Excuse me. So what are the conclusions of this long ramble? I think, these are my conclusions, I think that the first conclusion is that sympathetic layers are the best layers. I really think that ZFS is kind of the bomb. I really like Quick, and I really like Kubernetes. And I think operators are the future. I guess that's number two. Kubernetes operators and functions as a service are reslicing where the layers are. Remember, we're adding more layers to what we might call the stack. So, pods and Docker containers, sure. That's a necessary evil, in my opinion, to make it so that we can reslice where the layers are at a different location, and that's the routing and dispatch and the operator layer. Conclusion number three is you should absolutely watch Simple Made Easy by Rich Hickey. Again, as an engineer, your ability to make decisions and evaluate and trade off and do all these things really comes from the corpus of all the knowledge that you're kind of like soaking in. So this is, watching this presentation is one thing, watching that video is another thing, and then in your mind you'll be able to synthesize both together and make better judgment decisions in your job or at school. So, separation of concerns is overrated. That's why I say change my mind. And now I'll hold for shameless applause and then questions from the audience. Let's see. We have one microphone. So I'll hand the microphone for the recording.
Hi. I have a question. How to determine if your system is in the state when this reshuffling of layers is needed? How do you know that it can benefit? If there is any algorithm that can show you that you need some change or something like that?
Great question. So is there an algorithm or some sort of guidance or guidelines to know when it's appropriate to smash layers together, or maybe you need to tease them out? Definitely when you hit performance bottlenecks, this is the first indication that maybe you should start to rethink where the layers are drawn. In the historic examples, they weren't so obvious. So in the Quick example, I'm not really sure when that got started, but it's kind of easy to look at your technology stack, and unless you're asking really fundamental questions about how you're doing things, you'll never get those kind of revolutionary improvements. So Quick as an example, somebody must have seen the round trip times on SSL establishments, right? And seen how many back and forths it took to make the thing and said, well, what would it take to do 0 round trips? The ultimate connection. And I don't know, I'm guessing that they kind of went from there. And so in that case, they had money to throw at the problem, and the problem was real. They wanted to improve performance of HTTP. It wasn't like they were hitting a bottleneck per se, but Google just has an army of engineers to throw at that. In other situations, it's not the case. So in our individual companies, you're going to have to evaluate when you're seeing a performance bottleneck, and often, I believe that a lot of times it takes creativity and imagination to find those problems because they're not always obvious. Before John Allspaw, it was pretty normal to have a QA department and run all your code through QA and wait a day or a couple days or a week for them to get back to you and say good before it's deployed. Somebody had to question that. So somebody had to identify that as a real bottleneck instead of accepting it as a status quo for being industry standard practice. So no, I don't think that there's an algorithm. I think it takes creativity. I think it takes imagination. I think it takes just, I don't know, daydreaming, man. You can just daydream about what things could be. It's my best answer for that.
Thank you.
Yeah, this may just be splitting hairs, but wouldn't it be reasonable to say that rather than focusing on just immediately whether or not you should be merging down layers, the first thing to do is analyze the concerns themselves and ask, are these concerns in fact related? And then we should re-evaluate how the layers are put together based on our re-evaluation of the concerns.
I think I understand what you're saying. I feel like those are kind of the same. So I think the best example of what you're describing is with the file system. When you look at this, I think what you're suggesting is that maybe we should reconsider what the concerns are in the first place. So what are the concerns of a file system? And then maybe they kind of look the same. So maybe in this case, you might say that a file system is absolutely concerned with reliability of the data. It's absolutely concerned with confidentiality of the data. And I guess there's kind of an operability. It needs to be able to renew, slice and dice. On first glance, I don't think those concerns, they don't seem related, but definitely there are benefits when you connect the two. Yeah, I think you're right. I think the first thing to do is just look really hard at the concerns and see if they're really the same. So another example is within the quick example. When you look at the concern of encryption and error correction or error recovery, if you're imaginative, you may realize that there's a strong connection there, and that is the boundaries of the block cipher. So the block cipher might operate on 512 byte boundaries if you're just having a naive cipher. But then you might realize that in the real world, your transport is UDP and you might lose some packets. So maybe it'd be better if you could make the boundaries of the block cipher be the boundaries of your packets. Well, that kind of imagination, I mean, it doesn't take that much imagination, but you can see that there is a connection between encryption and error recovery in that case. So yeah, definitely a situation where the concerns are related. And yeah, over time you might realize that maybe they should be tightly coupled in some way. I know that's definitely a dirty word to say at Yelp, but tightly coupled, these things together does give you the performance of when you drop a packet, you don't have to discard any of the adjacent block cipher parts. You just need to replay that one thing. So yeah, that's a great point. Rethink your concerns first and look at them really hard and see if they're related before you just merge layers kind of linearly.
So, in all these examples of merging layers, when it's been successful with things like ZFS, tools have been built around these. When the layers are merged, tools don't exist to debug things like Quick.
Yeah.
ZFS, GDB on the kernel is your best effort for the most part. When you have encryption shoved back into Quick, you can't instrument OpenSSL anymore. Do we lose operations in this, and how do we decide how long to hold out in an inoperable world until merging layers is too painful?
That's a good question. I do think you hit on it, that how long, because I do think it's a function of time. We need to hold out for the kind of surrounding ecosystem to kind of catch up. In the case of Quick, there are definitely issues that you can't debug now, but I have faith that over time we'll get better tooling. I'm not exactly sure what the state of the art is on Wireshark decoding things, if you can inject things or Charles or any of the man-in-the-middle proxies, but certainly in a weird way, one of the reasons that the designers of Quick did it this way was to actually thwart the existing middleware boxes around the industry. So on the one hand, you might say, when is the industry going to catch up? Or is it okay that we've kind of thrown away all this tooling around TCP/IP, when in practice, that's the very thing that they were trying to reject, was the tooling that is middleware boxes, firewalls, and things that were kind of like screwing up TCP sessions. I do think it's a function of time. So it's one of those things where they have to build this in. So they have to construct this, they have to deploy it, they have to do the things. And then, our Android apps get updated and an open source implementation emerges, and then Wireshark gets support. So this kind of example takes decades. Likewise, ZFS also took a long time to develop. I don't really have an answer for how long, though. I think that the kind of like acceleration, the adoption curve kind of needs to be addressed on a case-by-case basis. If you're going to have a protocol, that's one thing. If you're going to be dealing with Kubernetes, it's one of those things that people can begin to explore it on their own without the rest of the industry, and they have to bite the bullet that this is going to be more complex to debug in practice. I promise at Yelp we will absolutely have outages due to this complexity, because we won't be able to keep it all in our heads at the same time. That's a cost, but at least that cost can be paid by individual early adopting companies and not necessarily in the industry as a whole. So yeah, that how long is really needs to be decided upon on a kind of company by company or engineer by engineer basis. But I think there isn't really a super great heuristic. It's kind of a function of your risk aversion and your need for speed. Like if you can identify that this provides you value, and you can trade that off, and you can say, yeah, if we move to Kubernetes, we can deploy a lot faster, or we can get code out faster, or we can like save a bunch of cache on these VMs. Then, yeah, it's like any other trade-off. You've got to like balance those cost and benefits things. But yeah, I see it as a function of time. Over time, Kubernetes will be the industry standard kind of thing. Quick, not so sure about. ZFS, I'm also not so sure about. It's tricky. I don't know. I'm just guessing.
So I too agree that separation of concerns is overrated.
Okay.
When you showed the slide about team,
DevOps?
merging teams and doing the DevOps thing.
Yep.
I'm curious what hand waving you do to get through an audit, through like SOC style auditing, in order to be able to say, oh no, there's separation of concerns here, even though we've compressed all this stuff into a thing that isn't where we. Yeah. So like, how is that happening?
That's a good question.
I have to sign those audit statements, and it's,
and I have to implement them.
Yes.
I am very familiar with SOX compliance, and I am one of the engineers who's responsible for making sure that we are compliant. It's not easy. Definitely, the laws and the frameworks we build are of our own design. SOX in particular is one of those things where it's more about being internally consistent than it is kind of globally consistent. So if you tell your auditors that you're doing things in a particular way and you're consistent with that and you're not breaking your own rules, it's generally good. It doesn't necessarily mean that you have to separate out into individual layers. It's not like you must. Like SOX doesn't care about this kind of thing. What they do care about is that code is being tested in the way that you said it would be, and it's being signed off in the way that you said it would be. For the most part, that usually just means that you need two humans. It's not necessary to have literally a team called QA. Again, SOX doesn't care about the actual implementation details of your compliance. They really care about internal consistency. So at Yelp, we get away without this because the code, because it's only deployed by a single team, you only need 2 sign-offs from that team. You don't need to break out of your team box in order to get code into production. Again, it's a function of a smooth process. Not only do we empower developers to do that, but they literally don't need anyone else. They literally don't need an operations team member to get their code into prod. So we've built it that way, but that doesn't mean that we're not violating. Doesn't mean we're violating SOX. It means that we've let SOX know that this is how we deploy, and this is how we make sure that there's no way for people to get code into production that's been rogue. So I hope that answers your question. It's absolutely possible. It's not necessary to hand wave. It's necessary to be diligent and deliberate about the decisions you make with your auditors. Granted, I'm only familiar with that and HIPAA, so there could be there's lots of stuff. So I don't know all details of all these things. So you do have to play by the rules. So you got to do what you can. But I don't think it's totally out of the question that you can get the benefits of layer smashing and still be legal.
I have a question. How do you think the evolution of the usage plays into this? For example, virtual machines were not really designed for this cloud-based, let's see how to frame this. But virtual machines, the reason they were designed was because if a hardware crashes, I can put it on something else. Similarly, TCP was only concerned with reliability. And now we are trying to do more things out of those systems. We are asking more things out of those systems.
Maybe to put what you're saying in a different way is that it's not as much as the concerns are wrong, it's more like they've changed, or maybe we've evolved what we're concerned about.
Right.
Okay. We still care about reliability as much as like you're correct that TCP/IP was originally invented to like save us from atomic warfare and get reliable missile launches. In the end, we're still cared about reliability to some degree with our packets. So the concern has evolved, but still there. Maybe a different example might be the concern of encryption. So encryption is a new concern. We didn't really have that before. So you can see I kind of stuck in layer 6, but like that's a new concern. So that's new.
Right. So SSL was forced on top of TCP because TCP was existing already. So now there's this new concern, SSL, which slows down things a bunch.
Yeah.
And then there is a new concern that mobile can switch from Wi-Fi to cellular, and you don't want to lose a connection.
Yep. I think that's a great point. That I think, not to put words in your mouth, but I believe that you're making the point that it isn't as much as that we're merging layers for fun. It's because there are new concerns that we didn't have before. I think you're right. I think it's kind of both. These new concerns are new requirements that we're putting on our stack with a model that didn't have them before. Yeah, I think that's the case with some examples. I think other examples like the file system, I don't know. I think it just depends. I'm a little skeptical of your VM example. Maybe VMs were, I don't know if they were originally designed to prevent hardware failure.
VMs were not designed for a distributed setting, right? That you are launching new services and elasticity, all this came after. VM was you're doing something, you don't want to lose context if your hardware goes down. So,
ironically, we do lose context when the hardware is down if you run your VM on Amazon. But yeah, that's something we kind of gave up, I guess. Yeah.
But in your example, you mentioned like this new approach gives elasticity. The operator can make sure how to launch MySQL. That was never a concern for VM.
That's true. Yeah, but in that example, keep in mind, everyone, when I say operator, I mean a Kubernetes operator. That's a piece of software. It's not a human. I agree that's a new concern, that a distributed world that we live in now wasn't what the world looked like when we had VMs originally. But I think even in a distributed world, I think that a hypervisor and a VM is still something that you would still have. It's not like, I think that's a kind of a standalone layer, and it's kind of like independent of whether you're in a distributed environment or not. You'd still want, a VM or hypervisor, rings in an operating system are still things the concerns that you have. I don't think they're mutually exclusive. I think that the operator, so the orchestration, the higher level kind of concept on the cloud is definitely the new thing. And that's the thing that layer smashing is happening because, I think it's happening because we are kind of fed up with humans doing that. We're fed up with humans picking servers out and, connecting them together. We want robots to do that when machines code. So yeah, that's a new concern, but I think it's a little orthogonal to the need of a VM or not. I don't know, just my opinion.
Thank you. Yeah.
Okay, last question, and I guess say goodbye.
Great. Thanks, Kyle, for the very insightful talk. A hand of applause for Kyle. And thanks all for coming out. If you have any questions, me and Abhilash will be hanging out here.
Thank you for organizing this.
You know what this reminds me of is like actually the American presidency. You know, like yeah, like just our government in general. Right?